talking about my project titled Challenging the Standard Paradigm of Thorne-Żytkow Object Formation. Okay, so what is a Thorne-Żytkow object? Or TZO for short. TZOs are theoretical stars powered by an accreting compact central object. And the central object in question is envisioned to be a neutron star or a black hole. And these objects were originally envisioned by Thorne-Żytkow back in the 70s. And instead of being powered by nuclear fusion like more traditional stars, they're powered by accretion onto the compact object. So how do they find stability? So TZOs are assumed to be accreting at the Eddington limit, which is the balance between the radiative acceleration and the gravitational acceleration. In the diagram on the right side, we see the radiative acceleration in the green color and then the gravitational acceleration in purple. So how long do they last and how can we find them? So first, to find how long they last, we can calculate their luminosity by assuming they are stable at the Eddington limit and approximating the neutron star mass to be about 1 solar mass, which is pretty approximate order of magnitude for neutron stars. And in doing this, for our general TZO case, that would give us a luminosity of 10 to the 38 ergs per second. And we can then use this value to find the temperature of its photosphere using the standard temperature relation for a black body, which then comes out to 7 times 10 to the 3 Kelvin for the specific value of the radius that I assumed. And then finally, we can figure out how long they will last by using this equation at the bottom to calculate their lifetime. And essentially, this equation tells me that the object will last as long as mass can be supplied, but that it will end once it accretes a large fraction of the entire envelope mass. So plugging in the mass of the envelope and setting the mass accretion equal to the Eddington luminosity, we get about 300 megayears for our very general hypothetical TZO case. So for this particular study, we examined a high mass X-ray binary system in a large Magellanic cloud called LMCS4. And for the remainder of this talk, I will discuss the story of LMCS4 within the context of TZO formation, starting from how it exists today and then extrapolating it into the future so we can see its final fate. So LMCS4 today consists of an 18 solar mass star with a 1.57 solar mass neutron star. And we decided to select LMCS4 to model as a potential TZO progenitor because the orbital period suggests that there is a gradual orbital tightening. And additionally, the primary is highly bound, which guarantees a merger instead of a successful envelope ejection. And if we take a look on the left, we see a plot showing the evolution of a star with the same mass, radius, and metallicity as the primary in LMCS4. So we have star age on the x-axis and radius on the y-axis. And the black dot represents LMCS4 as it exists today. And the green dot represents our model for LMCS4 after extrapolating it into the future, which I will later show how I use this as the initial condition for my simulation. And if we follow this blue line, we see the primary's radius growing with time, which is something we calculated using MESA, which is a 1D stellar evolution code. And the dotted pink line represents the separation between the primary and secondary, which was derived from observations of LMCS4. And in my work, I assume that the observed rate of orbital tightening is preserved in order to calculate the time of involvement. So, So to study the future of LMCS4, we use FLASH, which is a 3D hydrodynamics code, along with the initial conditions calculated using MESA that I mentioned in the previous slide. And so now if we take a look at this movie, as you can see, as you can see, the neutron star spirals into the envelope while disturbing a lot of the material, and then it finally lands inside of the core. And the simulation lasts a total of 13.8 hours. If we take a look at the right side, the top row just shows snapshots of the same simulation, and the bottom row shows the corresponding energy at those timestamps. And the orange represents which material is unbound, and the green is which material is still bound. And as expected, the envelope is not removed, although a small fraction of the envelope mass is ejected, but overall most of it is still there. And in this diagram here, we see the part of the envelope that is closest to the neutron star before it reaches the center of the star. And the yellow arrows represent the mass accretion inflow, and then the red arrows represent neutrinos leaving the envelope. And as material is flowing towards the accreting neutron star, it becomes heated and produces a hot region. And now there is a pressure-supported region that ultimately starts to oppose the infalling material, preventing it from falling all the way to the surface. And this creates a shock, which is labeled in white. And then neutrino cooling is essential as it allows the material to cool and be accreted by the neutron star. So a critical value of the accretion rate is when m dot is greater than or equal to 10 to the minus 4 solar masses per year. Neutrinos at accretion rates below this value cannot cool the material. So the plot on the right shows this very thing. We see time in hours on the x-axis and then mass accretion on the y. And the green line represents how much mass is accreted until the neutron star reaches the core, which is located at the blue dotted line. And then the red dotted line is where we expect neutrino cooling to happen. And as you can see, accretion happens above this critical rate, and the neutron star consequently accretes a total of 0.14 solar masses by the time it reaches the core. But this is a small amount and won't drastically affect the structure of the neutron star. So the goal of this plot is to show the formation of the accretion disk at the end of the simulation. So specific angular momentum is on the y-axis and then mass on the x-axis. And the blue dotted line represents the specific angular momentum required for disk formation around the neutron star. And as you can see, the specific angular momentum is above the critical line, and this condition is satisfied at all radii. And initially, we expect the neutron star to accrete quasi-spherically because there is not as much angular momentum. And then we expect a black hole to be formed when the neutron star reaches a mass of about 3 solar masses, which is represented by the pink shaded region. And then after this, we expect the central source to be a black hole surrounded by an accretion disk. And the diagram on the left shows the core collapse and how we can calculate the accretion rate after the black hole is formed. So shown is the core material around the central object, and we assume the core material loses pressure support and collapses, and then the code then follows the collapse semi-analytically. And yeah, when the object rotates, the material on the poles, which is in blue, collapses directly, while the material closer to the equator in green forms an accretion disk. So here we see the energy as a function of mass. There's a lot of lines here, but specifically the important part is if you look at the thick dotted green line, that represents the point at which the envelope is ejected by accretion feedback. And then the blue line represents the wind energy expected from feedback, while the pink line represents the binding energy. And the envelope will be ejected when the integrated energy is larger than the binding energy of the entire envelope. So to calculate accretion feedback, I use an efficiency of 1%, which is fairly standard. And yeah, and then after the simulation ends, the accretion rate will likely produce a jet, which is represented by this illustration here. So what sort of transient is this likely to produce? So here on the right, we see luminosity versus time in seconds, and the black dots represent thank you, represent standard long gamma ray bursts, and then the blue dots represent ultra long gamma ray bursts. And by assuming that the collapse of the core produces a jet, and that 1% of the jet energy goes into high energy radiation, I can calculate the broad properties of the expected transient. And as we can see, the transient produced by attempting to form a TZO is located between standard long gamma ray bursts and then ultra long gamma ray bursts. So what sort of object is left over? So we find that the luminosity is an order of magnitude greater at 10 to the 39 ergs per second than the standard TZO case. And this is because these objects are powered by black holes, which are more massive than neutron stars. And as such, the Eddington limit is larger. And then the photosphere temperature is about 10 to the 5 Kelvin, which is 2 orders of magnitude greater than before. So these objects are compact and very hot, and their temperatures are soft X-rays, and they would also be bright in the UV. And then the lifetime is estimated to be around 10 to the 4 years, which is 2 orders of magnitude shorter than the general TZO case. And this is because the envelope mass is small, and we can only supply accretion for a shorter period of time. And so we call these objects thin envelope TZOs because, as I have shown, the accretion feedback is likely to unbind the vast majority of the envelope. So I expect only a thin envelope to exist and power the central region through accretion, which is different than the original TZO model. And then how can we find these thin envelope TZOs? So here we see a plot showing the periastron versus the companion mass, and this displays outcomes from population synthesis models. And we see the vast majority of outcomes produce successful common envelope events, but then the black squiggly line at the bottom is the region where thin envelope TZOs would lie, which is where the neutron star would merge with the core. And so based on these population synthesis models, we expect a formation rate of about 1/1,000 thin envelope TZOs per year per galaxy, with a lifetime of 10,000 years, which essentially is just tens of candidates per galaxy. And then have we seen these objects already? So here is an image showing 2 ULX sources in the NGC 925 galaxy. These 2 sources have luminosities and photon temperatures that are similar to the ones that I predicted for thin envelope TZOs. So I'm not claiming that that's what these are, but this could be an interesting starting point for further investigation. And then with that, I will leave you with my conclusion slide. And then also I want to say, if you are interested in learning more, my paper is on archive along with a companion paper by my collaborator, which is at the bottom in yellow. Okay, thank you.